Welcome to the first theme session of this conference, in this case on multi-stratum designs. The first speaker will be Stephen Gilmore of Queen Mary in London, in the University of London, about multi-stratum response surface designs.
Well, thanks very much, Eric, and thanks to the organisers for inviting me. See if I can get the right one. So, first of all, I have to say to those of you who have been here since 3 weeks ago, I apologise that part of what I'm saying here will overlap with part of what I said 3 weeks ago. And I'll try to say something to wake you up when I'm saying something different. I've really only got one new thing to say, but I realise most people here were not here for that session, and so I'll try to explain a bit of the background. So, when I talk about multi-stratum experiments, I'm particularly interested in those in which the treatments are combinations of levels of several factors. So it's factorial treatment structures which include response surface designs, fractional factorials, all of these sorts of things. And in particular, I'm interested today in response surface designs. The multi-stratum aspect of it comes in when there are sets of experimental units, so typically runs of some process, think of runs of some industrial type process, which must all have the same level of at least one of the factors. So the textbook example is a split plot design, so everybody who knows, who's been to Design of Experiments course has probably heard of the split plot design, but here we're interested in more general multi-stratum structures. So for example, there can be more strata, split plot designs, or split plot designs, and so on. In this talk, I'm particularly interested in response surface models, so the treatment design will be suitable for fitting a polynomial response surface model, and in particular a second order polynomial I'll be thinking of in this talk. And so that immediately means that regular factorial designs are usually not the most appropriate. And the design will be small in the sense that each whole plot will typically have not enough experimental units in it, not enough subplots in it, to be able to have a complete set of combinations of the subplot factors. So, first of all, I'll say a little bit about multi-stratum structures, a bit more about multi-stratum, well, I've already said that to some extent, but multi-stratum designs. Then I'll mention different approaches to constructing these multi-stratum response surface designs, which are all in the literature, in the recent literature. Then I'll say, how do we compare designs? So if different designs are constructed by different methods, how do we go about comparing them? And how do we not go about comparing them? Then I'll make some recommendations. And in particular, I want to say something about some common methods for comparing designs which I think might be a bit misleading. So, when we're talking about multi-stratum structures, as I said, they typically arise when there are some sets of experimental units which must receive the same level of some treatment factor. So here's an example, an experiment which actually, I think this was one of the first that motivated me to get into this area. A biochemical engineer was interested in studying the effects of 5 treatment factors on the purity obtained, well, on several responses, but in particular the yield and purity obtained from a protein extraction process. So it's a typical lab-based experiment. Each experimental unit will be just a run of the same piece of equipment, and they'll do one run, then change the treatment, so change the settings of the factor levels, do the second run, and so on. So the 5 factors were the feed position, the inflow feed position, feed flow rate, gas flow rate, so that's all about things which are the mechanics basically of how things are going into the process, into the reactor, and then there was about the ingredients themselves, concentration of protein A and concentration of protein B, 2 particular proteins with long names which I didn't feel like writing up here. They could afford to do about 20 days worth of experimentation, and each day they could do 2 runs, so about 40 experimental units. But setting the feed position involved taking the equipment apart, changing the feed position, putting it back together again, and so that took up rather a lot of time. It was quite difficult and annoying. So, whereas the other factors they could change easily. So the other factors were just a matter of turning knobs basically to change them. So we should restrict the design so that both runs on each day should receive the same level of feed position. So that's what I mean by there being sets of experimental units, in this case the pairs of experimental units on the same day, the pairs of runs on the same day, which should receive the same level of at least one treatment factor, in this case the feed position. And so in the usual notation, so the sort of notation you get in GenStat, or similar to the notation you get in other packages, the unit structure has runs nested within days. So days are like whole plots, and runs are like subplots, or days are like blocks, and runs are like plots, whatever terminology you prefer. But the main effect of the feed position is completely confounded with the day effects. And these sorts of designs, these multi-stratum designs, usually arise from exactly these sorts of practical restrictions, some factors being harder to set than other factors. In this particular case, there's one hard to set factor and 4 easy to set factors, but of course in different applications there will be different numbers, and in some cases there may be some very hard to set factors, some fairly hard to set factors, and some easy to set factors. So if we're interested in fitting response surface models, so polynomial response surface models, say second order polynomial response surface, but we have these randomization restrictions which mean that we've got this multi-stratum structure with some factors applied at the whole plot level, some at the subplot level, or confounding so that some factors' main effects are confounded with blocks, however you like to think about it. How do we go about designing the experiment? Well, I think the first people to address this, at least in this context, were Draper and John in a 1998 paper who looked at some standard response surface designs, some central composite designs, and just looked at what happened if they used different orders of the runs. So how could they run them in particular orders so that the hard to set factors could remain at the same level for several consecutive runs. That wasn't really a systematic approach, but there have now been over the last 10 years, or 7 years, been discussed at least 3 different systematic approaches to constructing designs for these experiments. And they're sort of somewhat different in their philosophy. So the first one, I will describe as a stratum by stratum approach of Lucia Trinka and myself. Secondly, there's the globally d-optimal design approach, or d-efficiency, using a prior estimate of the ratio of stratum variance components. That's been developed by Peter Hoos and Martina van den Broek, and more recently by Bradley Jones and Peter Hoos, and maybe a few other papers in between. And then a different approach is what is known in the literature as equivalent estimation designs, but we've been talking about these a bit over the last couple of weeks, and I now actually think it's better to think of them as partially orthogonal designs of Scott Kowalski and his co-authors in a series of papers. And I'll say a little bit about what each of these approaches involves. So the stratum by stratum construction is completely general, so it's not just for split plots, it's not just for 2 strata, there can be any number of strata, U1 to US, so that might be like blocks, main plots, subplots, and so on, or the notation I prefer is actually to go from the bottom up and talk about experimental units, blocks, super blocks, and so on, super blocks. And there can be any number of factors applied in each stratum. So my notation is there are Fi factors applied in stratum I, and the unit structure in stratum I is labelled Ui. There may be no factors applied in some strata, of course. The way we build our designs is the following. We go through a series of steps for each stratum. Now, we tend to think of it as building it from the top, the highest level, so the main plots, down to the subplots, down to the sub-subplots, but that's not really inevitable. what matters is that we do the following steps in each stratum, or at least in each stratum in which there are some treatment factors applied. So first of all, we think of just the treatment factors applied in a particular stratum and choose a good treatment design for these factors, pretending there is nothing else. So choose a treatment design. That can be done by choosing a de-optimal treatment design, or it can be done by choosing a nicely structured treatment design, such as a central composite design. In each stratum, we then think of the units in the next higher stratum as blocks, and obtain a good block design for the treatment design obtained in the first level. So again, you can do that de-optimally if you want. So having chosen your treatment design, you now block it de-optimally with respect to the next level up. And then we combine the two in such a way that we get good estimates of the interactions between main plot factors and subplot factors, or generalizations of these two sets of factors. And then a final small step is just to then think about what happens if, so this is a bit like having trying to make the design resolvable or nearly resolvable with respect to super blocks above the blocks you're considering for stratum I. So in other words, for stratum I, we now think of the units in stratum I minus 2 as super blocks, and without damaging the design we chose here, we then try to, again, maximize some kind of efficiency, whether it's d-efficiency or any other criterion you prefer. For those of you who are just arriving, there are plenty of seats near the front if you want to come in. Sorry to embarrass you. Now, the idea of this approach is that it gives, again, depending on your optimality criterion in each step, it gives designs which are in some sense optimal or conditionally optimal as the ratio of stratum variance components, or alternatively the ratio of stratum variances, becomes large. So this is a notation. So this is a notation I'm borrowing from Hoos and Van de Broek's papers. Eta is sigma I squared over sigma j squared, where these are variance components in each stratum. So that's the variance component for blocks, for example, and the unit-to-unit variance. Now, why should we think about that becoming large? Well, essentially because that's the worst case. If this ratio is small, then in some sense any design will be good. And that's really the new thing I'm going to say in this talk, which I didn't say 3 weeks ago. I say we described it as an algorithm or a strategy without specifying exactly which optimality criterion should be used at each step. Although we did make particular choices for our illustrations, which maybe weren't the best choices and certainly weren't the most standard choices. You could, for example, use the D criterion at all of these steps. The second completely different way of building these designs is to take a straightforward or more mainstream D optimality or A optimality or any other kind of optimality approach, although it's mostly D that's used in the literature. And the idea here is that we think of the structured variance matrix for the observations, call that V. I've taken out the sigma squared just because it just gets in the way. And then think of a generalized least squares estimation. So the data from such designs are typically these days analyzed using REMO, residual maximum likelihood, to estimate the variance components, and then plugging these estimates into a generalized least squares estimator. And the variance of the generalized variance covariance matrix of the generalized least squares estimator has the form given here. And then we take the determinant of that, which is the usual D criterion. Except, of course, when we've got our data, we will estimate the variance components. So when we've got our data, we'll estimate V. When we're designing the experiment, we don't know what that estimate will be, and so we have to use a prior estimate. And as these algorithms are described, the usual method is to just use a point prior estimate, although integrating over a prior distribution is conceptually straightforward. Then we search for optimal designs using standard exchange algorithms. but they're modified to make sure the design obeys the randomization restriction. So it's like an exchange algorithm where you have a starting design, say a randomly chosen starting design, and then you simply try swapping points in the design with other points, which are usually in a candidate set of points, and you keep swapping and accepting improvements until it converges. And typically you try that several times for several different starting designs and pick the best one. More recently, Bradley Jones and Peter Hoos have come up with quite a neat algorithm which speeds that up considerably by being what they call candidate set free. So the usual method is to have a list of candidate points, which will be a very big list of design points, and then try exchanging points in your current design with points in the candidate set. They basically don't have to list their candidate set, and so that saves a certain amount of time, quite a lot of time it seems, and speeds up the search a lot, which then means you can try more random starting designs and be more certain of getting an optimal or very close to optimal design. Then the third approach, what I call the partially orthogonal designs approach, the authors of this series of papers use several different methods to construct the designs, and they describe the main aim as being to ensure that ordinary least squares and generalized least squares give the same estimates. But actually their conditions are much stronger than that. They ensure much more than that. So they ensure that all linear and interaction effects are estimated orthogonally to the block effects in the next higher stratum. So that's why I call them partially orthogonal designs. And they ensure not just this equivalent estimation for the second order polynomial model, but they also ensure they get equivalent estimation for all submodels of that model. So if you drop some terms from the model, their methods of construction, or at least in the first paper and the last paper, ensure that this equivalent estimation property remains. The designs they obtain can look a bit odd at first sight. So for example, you can get one whole plot in which every observation has a center run. So if you've got, say, 3 levels of each factor, -1, 0, and +1, in some of their whole plots, every observation has got 0, 0, 0 for all the factors. So they repeat the same treatment for every subplot within a whole plot. So what are the advantages and disadvantages of the methods? Well, the stratum by stratum method, I think the advantages are, first of all, that it's completely general for any multi-stratum structure. It's not just for split plots or just for split plots. It's for any multi-stratum structure within the class I've described without any other modifications. So that, I think, is an advantage for the user, maybe a disadvantage for us, because it meant we could only write one paper rather than writing a separate one for each special case. The other second advantage, is that they don't depend on prior estimates of variance components, and they're robust to different values of variance components. So you don't have to specify a prior estimate with variance components, and your design, in a sense I'll show later, the design you obtain is pretty good whatever the values of the unknown variance components are. And it's in some sense optimal within each stratum. The de-optimal approach to design construction has its own advantages. First advantage is that the designs you obtain are de-optimal, which is fairly obvious perhaps, but important. And in particular, the de-optimal in some global sense, so not just in the stratum by stratum sense that these designs are de-optimal. They take account of prior information. So again, it's the usual thing. This is the advantage that it doesn't depend on prior estimates. This has the advantage that it does depend on prior estimates. Which is better? If you've got prior information, surely you should use it. And fast implementations available in commercial software is an advantage, as long as you've got the right package. The designs constructed by the partially orthogonal approach, I should say the packages jump, which Bradley Jones will tell you more about, should you so wish. Partially orthogonal designs, on the other hand, have some advantages as well. Also, they don't depend on prior estimates of variance components, and they are robust to different values of variance components. And their own advantage is that they allow pure error estimation. So you can estimate the whole plot pure error and the subplot pure error, at least from some of these designs. Each method also has its own disadvantages. The stratum by stratum method we have found is not very easy to implement, so we did make programs available, but it seems that they're impossible for anybody to use apart from us. So that's a definite disadvantage. You can't write down in a single formula the criterion which is optimized. I mean, this is again partly because we were trying to make things as general as possible, trying to make it an algorithm for whatever criterion you wanted. But by doing so, it means that it's not specific to one particular criterion, and it's difficult to write down exactly what you're optimizing. A possible disadvantage is that it rarely produces designs which have this equivalent estimation between generalized least squares and ordinary least squares. And I need to speed up a bit. Disadvantages of the d-optimal approach, well, they're d-optimal. I mean, why would anybody want a design to be d-optimal? Perhaps more importantly, it's not really d-optimal. It's only d-optimal if the ratio of the variance components is known. If it's unknown, what are the real properties? And for practical use, it's not quite as simple as it sounds, because it's probably recommended that you find optimal designs for several different values of the ratio of variance components and look more closely at them. And they rarely allow pure error estimation. Partially orthogonal designs are really inefficient. Let's say they're spectacularly inefficient, almost as if they're designed to be inefficient. And you can find more efficient designs which have got many of the same good properties as these designs have. So how should we go about comparing designs? So let's say we've constructed designs by all three methods, or by whatever methods. We've got some candidate designs. How do we go about comparing them? If different designs are optimal for different values of eta? Well, what you might do is to look at the relative efficiency in some sense, or the efficiencies in some sense, as the ratio of variance components increases. So this is, for example, this is taken from Peter and Martinez's first paper. You can see some different designs are optimal for different values of the variance components. Now, I decided to illustrate my point that I find D efficiency too difficult to understand, so I decided I would illustrate it using A efficiency with some artificial examples, because at least I know what A efficiency means. So let's say we've got two candidate designs. One of them is optimal for small values of eta, and then the other is optimal for large values of eta. So which is best? Your first thought might be the red one is best, because it's always at least 85% efficient, whereas the black one can be less than, well, I don't know, 10% efficient or something. Now the first point is, if you're looking at that for different eta, why do you stop at 5 or 10 or wherever? Why do you stop at any particular point? So it doesn't look quite so good if you go up to eta equals 10. Second point is, efficiency is the wrong thing to look at. You really have to look at variance rather than efficiency, because variance is what translates into pounds or euro or dollars or whatever. And if you look at these two designs in terms of the value of the A criterion, which is the average of the variances of the parameter estimates, it looks different. So the red design now looks pretty bad because its variance is much higher. The black one, okay, here it's got higher variance, but here any design's got a low variance. We can actually look at all values of eta by looking at the intra-class correlation, or intra-block correlation, rho, which is just eta over 1 plus eta, and then you can go up to infinity for eta, or 1 for rho. And if you look at these two designs on that scale, they look like that. So basically, nothing's happening except for big values of rho, and then the red design is much worse than the black design. And just to show that, I've also plotted the difference. So you can see that this design is optimal up to about here, but you're only getting slightly lower variances, whereas beyond this point, the other design is optimal and you're getting much lower variances. Can calculate. Now let's think about perhaps think about being a bit Bayesian, or just taking an average. If we look at the average of the A criterion values over a grid of values of rho, the comparison depends on how fine the grid is. So this is the design that was red previously and the one that was black previously. If you take a grid just going 0.1, 0.2 up to 0.9, you find that this red design is optimal, but if you take a finer grid, the black design becomes optimal. And that's driven by what's happening at the top end of the grid. So even if you start your grid higher up at 0.2, you still find essentially the same. So the problem here is that the comparison between designs depends almost entirely on the upper limit of plausible values of the variance component between whole plots. So if you're Bayesian, so it's basically how high is your prior? How high does your prior allow eta to go? And in fact, it's even worse than that, because if eta is high, the GLS estimator with an estimate of eta will be worse than the apparent GLS estimator with a known eta. If you're using what's usually sometimes called a Bayesian optimal design approach or average optimal design approach, where you sample from a prior, so you specify a prior distribution for eta, sample from that, and then evaluate the criterion at each point sampled, that's particularly dangerous here because the design efficiencies are so dependent on the extremes of the prior distribution that if you do it at different times, it just depends on, almost just depends on what the largest value sampled is. So, sorry, I'm running out of time. How should we choose a design? I think we should either think of the largest plausible value for eta, then double it, and then use a JUMP or some other program to find a D optimal design or an A optimal design or whatever optimal design you want. Or use a stratum by stratum approach with your favorite optimality criterion. And some other areas that might be worth investigating is whether we can improve. So the stratum by stratum algorithm is a bit like choosing a D optimal design, treatment design, then de-optimally blocking it. We could, instead of doing that, choose a de-optimal blocked design. So it's the same argument with block designs as here. So maybe we can improve that. Perhaps the de-optimal searches could be changed to encourage them to look at the limit as eta tends to infinity. And perhaps we should think about other methods of estimation apart from GLS. Finally, this is just something that came into my head this morning. Since it's a bit strange, this dependence on the extremes of the prior, can we think of modeling the upper tail of the prior by some sort of extreme value distribution? Is there any sense in doing that sort of thing? And would it make sense to integrate over that or somehow average over that to get the optimal design? Okay, thank you. I'm sorry for taking up too much time.
We still have time for a couple of questions.
Steve, I'm curious, where would you get information for an actual prior? Would it be elicited or would you just guess?
Well, I mean, in typical industrial experiments, you've done work on the same process before, so you would probably look at historical data, and so a mixture of historical data and eliciting it from the engineers. And I think the traditional view is you don't have to be very careful about that, but I think what I'm saying is you do have to be much more careful about it than might perhaps be realized.
Well, it seems to me then that's the appropriate approach, that if you've got information and you can develop a prior that's really meaningful, then just go ahead and use it. And you could do a sensitivity where you've got 2 or 3 priors that reflect different viewpoints.
Yeah, well, although, as I say, it does also depend on how you sample from the prior. So because it depends on the tails of the prior.
Everything depends on the tails of the priors. That's what I mean. If you do a careful job of modeling the prior, and then maybe there's some disagreement between you and the area experts, you can write down a few of them and see what you get.
One other question. Well, I'm sorry that I cannot.
Hello.
There's a very conspicuous fellow.
Yeah. Steve, what's going on with the partially orthogonal designs in terms of the quadratic effects?
Well, the designs built by Kowalski and his co-authors, they're basically putting zeros in. So they're only having zeros and non-zeros in subplots together when there's a zero in the whole plot. If there's something other than zero in the whole plot, either everything's zero or nothing's zero for all the subplot factors. So it's the simplest, it's really the simplest way you can think of getting this equivalent estimation.
So why do you use the word
Okay,
partial?
I'm sorry, but I cannot allow an extension of this question. Thank you, Stephen, for your clear overview of the various types of construction methods. Let's thank Stephen once again.